Welcome, everyone. So today we're going to be talking about quantum mechanics. This lecture and the last lecture, quantum mechanics and classical circuit theory, are kind of formatter. They're the two necessary ingredients to begin talking about quantum computing proper. The lecture before that, kind of lecture zero, was about state, information, and computation. That's more about a theoretical framing device for the entire course. Those are concepts that are going to come up time and time again. They're motifs of the course. And I want you to think about everything that's kind of said throughout the course in terms of those things. So this course and the next this lecture, quantum mechanics, and the previous one about classical circuit theory are necessary ingredients to start talking about quantum computing. If I just started talking about quantum computing and like the Deutsch algorithm and things like that without talking about quantum mechanics or without introducing you to classical circuit theory, you'd have no idea what I was talking about. Nothing would make sense. No one would learn anything. So that's why we're talking about these things, right? Quantum computing is a diverse field. It encompasses a lot of fields, a lot of areas of study. So that's why these things that don't necessarily seem like quantum computing directly are going to be discussed in this course. So quantum mechanics, don't worry, it's a fascinating subject. So it'll be a joy for me to talk about, and I think it'll be a joy for you to learn as well. So quantum physics, to talk about that, and for you to really appreciate how groundbreaking it is, we need to start talking about classical physics and the rules of classical physics that quantum physics really breaks. So, how do we encapsulate classical physics in the rules that physicists thought the universe followed, but quantum physics told us no, it doesn't follow those rules? Well, we talked about this a little in the first lecture, but we kind of have a state, and it has these kinds of initial conditions, right? We could talk about the particle again, but perhaps we could do something more interesting. Let's do two particles. No, the particle is just a good example. You know what? I'm going to stick with the particle. So we're sticking with the particle, and it's going to have this, right? It's going to have position and velocity again, and essentially it has initial conditions, right? It has a state space. State space. It has position and it's got velocity, right? And the idea is if we specify these things at a given time, t at a given time, t0, right? T0, then they're just known for all time. That's sort of the idea. That's very classical. And it's something that physics was kind of founded on from Newton on until classical physics in the 1920s started kind of tearing these ideas apart. So, um, specifically, how it's determined for later times is the laws of nature. And in the case of this particle, we're going to have F equals ma telling us that. But this is kind of the classical paradigm, right? There are a couple of other things that are tacit here, which is that we can measure at any time to verify that this is true. We can measure the position, we can measure the velocity at any given time, and it's not going to affect the system in any way. Hint, hint. In quantum physics, this is no longer necessarily going to be the case. Um, this is kind of the classical paradigm that we're talking about here. Now, um, again, hint, hint. This will not necessarily be the case either. This first thing that we'll have a state space where all these things are necessarily going to be determined. Um, But I'm not going to tell you exactly how quantum mechanics breaks these rules yet. I'm going to let you kind of figure it out and see it in detail through a couple of experimental results. One specifically, the double slit experiment, pretty much says it all, I think. There are a couple of other ones like Einstein's photovoltaic effect kind of showed us that energy and momentum and all these things were quantized. There was the Gerstein experiment with the silver molecules and the quantization of their spin and things like this. But I think the double slit kind of says it all for the purposes of this course. Sorry about that. So what I'm going to do is kind of give you this classical picture, and then I'm going to show you the double slit experiment, and I'm going to show you exactly how we seem to be in a little bit of having some contradictory issues here with this classical picture. So bear in mind the classical picture while I go through the double slit experiment with you. Okay. So double slit experiment. Essentially, we have an electron gun here. It just fires electrons. The way you would actually accomplish this would be just you could just heat an element. If you get something hot enough, it'll just start ejecting electrons. That just happen. There'll be thermally random electrons will be ejected. So you can just heat up an element that won't melt. It'll get white hot and start randomly thermally ejecting electrons. If it's red hot, It'll be ejecting low energy electrons, whatever. So then we have the all important when the wall here, and it's going to have these kinds of like slits in it, right? These little like windows that can open and close. And for this experiment, we're going to have two, hence the double slit experiment. And then we're going to have a screen, a back screen here, and this is going to function as a detector. So essentially, it's going to detect whenever electrons impact it. Functionally, you could use a scintillator to do this, right? It fluoresces every time an electron touches it, and then you can use a camera that takes a picture. That every single time it scintillates, that's recorded by a camera, and then you can just count it. And what we're actually after here is the probability as a function of x, where x is this axis here, um, that an electron is going to impact this area. So we can count and divide by the total number of electrons, right? How many electrons impact, whoops, I don't know how that happens. All right, the number of electrons that impact as a function of x divided by x is going to be equal to that guy there. So that's what we're after. That's the problem. That's the thing we're after. Now, this is the way we frame it in notes. Is the best way to frame it is when we look at experiments. The actual raw results, theorists are looking at pictures of things that we already kind of know about. So there are two things we know about that really pop up in this experiment and kind of show their face. But it turns out electrons are really like neither of them, but their signature kind of shows up in this experiment. And the two things are particles and waves. Probably heard of wave particle duality. That's usually given short shrift and it's a little pop sciencey, but it is kind of wave particle duality, but it's not, they're not on equal footing and they're really, electrons are neither one of those things. So I'm just going to give you the straight experimental results. But first, you're going to need to think about how a particle would act in this situation and how a wave would act in this situation. So let's imagine that electrons really are particles. So what would particles do here? What would particles do? Well, you'd essentially be firing these little pellets. You can just think of them like bullets now. This is nice and easy. Like BBs, pellets, whatever. And you can fire these at different angles, or this could move either way. Doesn't really matter. The idea is that these could be firing in random directions, and we can open and close these windows. So um, essentially, if we only open one window here, only have one window open here, what's going to happen is with a uh, random probability, it's going to specifically look like a bell curve. With a random probability, these electrons are going to hit here. So the probability is going to be um, a bell curve, right? Because it's just a normal curve. That's just how probabilities act. Nothing special there. But basically, we're just going to have a bunch of bullets firing randomly. Most of them are going to deflect off again. Some of them are going to make it through the window. And it's basically going to be like this kind of effect, like a fan effect, right? Like kind of a splattering out here. And mostly this is not going to happen. Mostly this is going to happen. This will be less likely out here. This will be more likely in here. That's just kind of how particles act, right? And it's crucial that we're assuming that they're not going to be ricocheting off of each other, right? These electrons will not interact with each other. They won't bounce into each other and ricochet. We can send them one at a time if necessary. Okay, that's really that's we can all intuitively understand that. No further explanation necessary. Let's open in both windows at the same time. What's going to happen? Well, again, this isn't real complicated. Like um, everything that was ricocheting off before is now, instead of ricocheting off, going to just go through. So you're literally just going to get another same bell curve here, and they're just going to add, right? They're just going to add probabilistically, right? They're just going to add. So, I mean, this is all really straightforward. We all know how these things act. We see things like this pretty much every single day. This is what we're familiar with. Okay, so this is how particles act. Um, let's put it down in print here. Probability of X plus the probability of Y, or probability 2, right? So when we open one window, the probability, and then close the other one, if we only open window 1, that's what probability 1 means. If we only open window 2, that's what probability 2 means. If we open both at the same time, let's just call it 1, 2, that's what that means. Okay, so this is what particles would do, right? Okay. What would a wave do? it would be very, very different, right? Because waves interfere with each other. They don't just ignore each other. When you have two waves, you've probably seen this. Think about any kind of wave you're familiar with: ocean waves, light waves, sound waves, any kind of waves whatsoever. They don't ignore each other. First off, waves fill all space, right? Second off, they don't ignore each other when they intersect, when the wavefronts intersect. They have effects on each other. So let's see what would happen in this experiment if we had waves, and if electrons happen to be waves instead of particles. Okay. So we send out an electron and we only open one window and we close the other window. Um, we're essentially going to get the same effect for now, right? Let's just say we're going to get the same effect. It doesn't really matter. We're just modeling these as normal distributions because that's kind of how probabilities act. The important thing is the differences when we open different configurations of windows. Okay, so we send one through. Um, it looks like that, probability one. And then now let's open the other window. Right, now both windows are open. And we have these two kind of things. They're both coming through here, right? All right. Once we open both windows in this region, they're going to interfere. They're not just gonna add the way that particles did. So this is what would waves do. What would waves do? They're gonna interfere with each other, right? Now, the fact that waves interfere, uh, how do they? We talked about qualitatively just before how the fact that they do interfere, but how do they specifically interfere? Um, Well, you can think about waves like this. This is the way I always think about wave interference. You have a parent pushing a child on a swing, right? You have a child on a swing here, and you have a parent pushing the child on a swing. And let's say there are two parents, the mother and father, or father and father, whatever, it doesn't matter. The two parents pushing father, or two people pushing a child on a swing, right? And if they're pushing at the same time, exactly with the same at the same time, um, the force with which they push reinforces and the child goes much higher, right? But what if one is pushing when the child is coming back? What if they're pushing out of sync, right? Then you actually have this kind of interference in deconstructive manner. That's intuitively what you should be thinking about, right? If, for example, the child is coming in and the parent is pushing out, they deconstructively interfere with each other. They cancel each other out, and the child will go less high, right? That's all wave interference really is: constructive versus deconstructive. So, specifically quantitatively, how are these waves going to act when these wavefronts meet each other here? Well, modeling the waves as cosines, which is fine because all waves mathematically take that form. If you have two waves, which is, we'll call this wave one coming through here, and call this wave two coming through here, and they're both cosines. They're going to both have the same amplitude rate because why would they not? There's no reason to believe otherwise by symmetry. Or rather, this is what we want: frequency of t, right? Frequency of t. All right, so this is frequency times time. And the thing is, if all was equal, if there was the same distance to this point as there was to this point, see that distance there? This is a bigger distance than this is by the Pythagorean theorem. So that means this actually is going to take a little while longer to get there. And because it takes a little while longer, it's going to be out of phase. And because it's out of phase, that disappeared. But it's going to be like the parent of the swing, right? They're going to deconstructively interfere in a way, and this is actually going to be a little lower than it was. So we're going to get this kind of interference pattern here that you would not see with particles. You wouldn't see that kind of interference with particles. Um, yeah. So what would it actually look like? Um, well, let's do this again. Probability one plus probability two, when we have both windows open, is going to pick up now an interference term instead of addition. Um, Probability 1 for probability 2 plus cosine cosine of P1, P2, I believe. Right. So it's actually going to pick up that interference term there, right? Instead of just adding. I think that's how we're doing it. Where this can be negative, right? Because cosine goes between -1 and +1. So in practice, what you actually get is instead of this like bigger bell curve in terms of particles, for a wave, you kind of get these like really bright spots and then these like troughs, right? These troughs where it's dark. You get like a wave, right? It's wavy. So that's how a wave would act. If electrons were waves, this is the kind of thing that we would pick up here in this experiment. So which are they? Are they particles or are they waves? Well, there's definitely some subtlety here. It turns out that when we look at them, they're particles, and when we're not looking at them, then they're waves. And again, this is a very confused concept in quantum mechanics. That observations by us are somehow special. They aren't. Any kind of jostling of a quantum system will cause the same sort of collapse. We talked about the collapse before, right? Um, I believe we talked about collapse. Yeah, in classical probability, there's a collapse as well. So we talked about that. So any kind of if you have a quantum system and it's just kind of sitting there unperturbed, it evolves deterministically. But if you observe it in any way, the way that we look at it to try to be like, what's its energy? Let's take a measurement, or let's look at it with a microscope and bounce a photon off of it, right? That will actually cause like a collapse. And in that case, everything looks like particles. But in the case where we just don't observe the quantum system and leave it alone and don't look at it and nothing interferes with it, you maintain the quantum coherence of the system. It acts like a wave. That's the high level overview. So what does that actually mean in terms of this experiment? Well, if you have this electron gun here and you're shooting out these electrons, first off, let's send one electron out at a time. Yeah, one electron out at a time, and you have this window open here, right? What actually happens? Well, if we're not observing it, you actually get the wave interference, right? You get the brightness, and then you get the troughs, and then you get the brightness, and then you get the troughs. Okay, so it looks like a wave when we're not looking at it. That's very strange. Stranger still, let's have both windows open. Both windows are open now. So we send only one electron at a time, right? Only one. Okay, and we don't look at which window it goes through, right? Right. So we still get these wave interference here. That's extremely strange, right? If we had two electrons and they were both waves, they could interfere with each other because they're one's going through one window, one's going through the other, and they're out of phase. But one electron should not be interfering with itself, right? That doesn't make much sense. So this is kind of your first taste of quantum strangeness. If you send one electron and you don't look at which one of these windows it's going through, you actually still obtain these interference patterns as if the electron has somehow simultaneously gone through one or both or neither gates and we have no idea, and it's interfered with itself like a wave. So there's your first taste of quantum strangeness. This is very, very odd. Um, Stranger still, if we look at this and we say, well, this is very weird. I don't like this at all. Let's look at this electron and pigeonhole it and see which window it's actually going through. So we make an observation and we say, okay, we know now. It went through window one. That's okay. It went through window one. What happens? Well, it's actually like a particle again. This interference completely disappears, and because we observed it and perturbed it and basically decohered the system, by bouncing a photon off of that electron, we've actually erased this wave interference. The electron basically has changed as a result of our measurement. We've somehow affected. Remember in the classical picture, I said you can measure a system as much as you want; it doesn't change. I can measure the energy or temperature of a balloon as much as I want, and I'm not collapsing a system, right? The balloon doesn't collapse into a state of a new balloon with new atoms in new places or anything like that. None of that weirdness happens. In this situation, if I actually look at the electron and see which window it went through, I no longer see this wave-like kind of interference, and it now just acts like a regular particle. Um, This is just the way nature is. You may object to it philosophically or in some other way, but at the end of the day, this is just kind of what nature says, and in physics, that's the last word. So, um, yeah. So we have this kind of wave-like particle duality here, and that's what it actually means. So like, let's put a little bit of theory to this experiment now, right? We have the experimental results, and now the theorists have to look at them and kind of put some sort of theory around it and drape some sort of math around it to get some consistency logic. Excuse me, consistency logically and mathematically, so that we can actually use this to make predictions about nature and make sense of nature. So let's kind of attempt to do that here now. Um, so we have this wave. Okay, once you have a wave here, um, because the particle does seem to be a wave, and the wave specifically, we're going to call it psi from now on. Psi of x. That's what this wave is that we've been talking about. Um, and if you look at it, it's still a wave, but it collapses to a specific point here, where specific probability 1 equals 1, and that means the particle is definitely there. So that's a particle. So the wave collapses to a particle. You can think of a particle as an infinitely thin wave with an infinitely high probability. Well, not infinitely high, 1, right? What we do is we kind of normalize this. This is called the Dirac delta distribution. But this is kind of what the collapse looks like mathematically. But if we don't look at it, we have a wave. So this wave seems to be pretty important, and as long as we don't disturb a quantum system, it seems to still evolve deterministically. So we've recovered something from classical physics. There's still this F equals ma sort of thing where the system actually will evolve deterministically as long as we don't touch it or jostle it or make any kind of observations on it. So let's kind of hold on to that and try to go from there. And we are eventually going to get something like F equals ma. It's called Schrodinger's equation. It's how the wave evolves. But how can we derive it? Well, theorists look at this and they said, a wave has to take a mathematical form, right? We know it's a wave. It acts like a wave. We got that from the experimental results. So we know it's going to look like, a cosine or a sine or something like that. It doesn't matter. They're just shifted they're just a phase shift away from each other, really. So it's going to have to look like this, right? Pretty much it. Or kx rather, plus this, right? So it's going to have to look like that. And we also know energy is going to be conserved. And I mentioned this before, but Einstein had actually done the photoelectric effect by this point. So we know that energy has to come in these discrete little packets like this. And that's frequency. And we know that momentum also has to come in these discrete little packets of momentum instead. So now what we can do is write this in terms of the energy conservation relationship. And we can kind of force this to obey energy in equational form and see if hopefully we can get some sort of a equation like F equals ma that essentially forces this wave to evolve in a way that energy is conserved. So it's going to be kind of like our first stab at this. We're going to say we want our F equals ma to make sure that this wave changes in a way that energy is conserved. That's very reasonable and sounds a little trivial, but turns out it's going to work. So let's just do it. Um, right. So we want, trying to remember how this goes. Um, right. We just write down energy conservation, right? That's all. Um, squared. T squared over 2m. Okay, so this is kinetic energy, right? P squared over 2m is equivalent to kinetic energy. And then there's hopefully some sort of potential energy in the term as well. Energy is going to be equivalent to energy, and we want this to be conserved. So let's multiply this all by a wave function, or rather, uh, actually, let's do the time. Let's do time dependent, actually, in our derivation. We actually want this to be the way that it evolves towards the future. I like this derivation better. So what we're trying to do is figure out how the thing evolves, right? So how does the wave function evolve towards the future? Hopefully in a way that conserves energy, right? And we want this to also equal a constant. Okay, so now we multiply this all by the wave function. Oh, whoops. Yeah, we multiply this all out by the wave function because it has to be involved in the equation, right? So we know that. And ultimately, that's the way we get this time evolution operator here operating on the wave function itself, right? We can add a t in here. It's implicit. I think it's pretty obvious that there should be a t. All right, so, right, we got this now, and this is our requirement that it has to look like this. And what we want from here is we want some sort of differential equation because we like the laws of nature to obey differential equations, and in physics it just makes sense for everything to be continuous. We need a differential equation that's going to enforce this condition. What should it look like? Um, well, we have to come back to uh, this form of the equation. What will it look like? So, oh, I've skipped a step here. That's how we get that, right? So the first partial derivative with respect to t will give us frequency, right? That's where we get energy from. We want h omega energy. Sorry about that. It's been a while. So yeah, so you want the first derivative of that, and then we have kx here. So in order to get kx squared, right? The k is the momentum, by the way. Uh, there you go. In order to get that, you want the second spatial partial derivative operator. So in order to get this result here, we're going to do this. Second square plus, this is fine the way it is, equals, to get HW, we want this, which I've kind of skipped ahead here. Seen this derivation a lot. Right. So this looks a lot like the Schrodinger equation, except that there's negatives involved here. H bar. This comes from the fact that when you take this square, this negative has to pop up. I dropped a negative somewhere here. And to take this square, this negative has to pop up. Because we have negatives, we need to introduce an imaginary number. That's all. So this is the main event here. This is the Schrodinger equation, right? This is RF equals MA. Schrodinger. Sorry, I'm having a little bit trouble with writing today. Schrodinger equation. Right? You can see that there. Good. So in the Schrodinger, in quantum physics, we're not all is lost. We still have a kind of an F equals ma analog here. As long as we don't touch the system or mess with it at all, and we're not looking at it, it will still evolve deterministically, according to this equation right here. We can solve some example problems and stuff like that to see how this actually works in practice. But this is good. This is a triumph. So theorists were able to come up with an equation that will allow us to deterministically evolve our wave function. And as long as we don't make any kind of observations on it, which kind of seems like a big ask, it will deterministically evolve according to this, right? Now, this wave function here will also break with classical physics in another big way. In classical physics, when we solve our F equals ma, we get deterministic results. We get that the particle is here and its velocity is there. Not so lucky when it comes to the wave function. The wave function is actually not going to give us that. What it's going to give us is a probability distribution, as we saw in the experiment, right? So it's going to tell us that what our probability of x is. By the way, specifically, it's the square of this because these, there's imaginary numbers involved and position can't be imaginary and such. So the square of the amplitude of the wave function is going to be telling us these things when we do actually make an observation. Um, so that's another one of the huge breaks with classical physics is we're not allowed to know deterministically necessarily. You can get a wave function that does tell you deterministically. I think I showed you before it's in the case where you have this Dirac delta distribution. And in fact, after you make that measurement, as I showed you, it will collapse to this. That's the one wave function that will give you a deterministic result. Say, yeah, with probability one, you are in this position. But if you leave it alone and you don't observe the quantum system, it can continue to evolve to a new wave, right? Whatever. And this in no way will give you deterministic results. This says that there's a probability that you could be here. There's probably you're not here. The electron could be here, maybe not here. 10% chance here, right? It's all in all, that's all you get. That's the most information that you will get out of your wave function is this probability distribution. So when we get into quantum computing and we're talking about these bits, remember I talked about classical bits and they're definitely a one or they're definitely a zero. That's not going to be the case anymore when we get to quantum computing. And that's by design. We want that, right? We're happy to have this kind of thing. In physics, this is very unfortunate in a number of ways. In computing, this can actually be used to make very powerful algorithms that can outperform classical computers in a lot of really awesome ways. That's why we use it. Because basically these probability waves can act in a way that classical computers can't, and can solve a lot of really cool problems in a lot of really cool ways that we would have to brute force. If you kind of think about a maze, consider a maze for a moment, right? A computer would have to brute force that maze. There are cleverer algorithms, but it would have to brute force it, have to check every single little way out of the maze until it finally gets the right one. These probability waves can kind of search over all space at the same time and in parallel consider all these possible things and then return a solution to you. That's kind of a heuristic way of thinking of why the quantum advantage, why we want to use quantum computers. So in the next lecture, we're going to be start talking about qubits. Now that we've talked about quantum mechanics, I'm allowed to talk about qubits now because it will make sense. Remember when I said the bits will not be a 0 or a 1? I said maybe both, maybe neither, maybe one, maybe the other. Now you kind of get what I'm talking about, right? You see that these states are just probabilities. What we're actually going to have is it's not going to be a 0 and it's not going to be a 1. What it's actually going to be is the qubit will be in a linear superposition of possibly one or possibly the other. You're going to actually have something like this. Maybe it's a 0 with probability a squared, and maybe it's a 1 with probability 1 squared, or a b squared, sorry. You don't know which is which. Or sorry, until you make a measurement, it's in this state. And when you're not making measurements, that's when the quantum gates are doing their work. So you want the quantum gates to kind of entangle these with other qubits, and you want them to transform them into new states and rotate their phase and all this kind of stuff. And then at the end is when we take the measurement and collapse it to something. Okay, you don't want to disturb it because otherwise you're undoing all the work that your quantum gates are doing in the first place. So that's the excitement and promise of quantum computing that I can finally talk about now that we've talked about quantum mechanics. So you guys should be excited now. All right, I'll see you next lecture.